Welcome to Lecture 5 of Introduction to Quantum Field Theory. In this lecture, I will finish up with the interpretation of quantum mechanics as a path integral. The reference for this lecture is still the textbook by Leine and Vuorinen, Basics of Thermal Field Theory, Chapter 1. In the last lecture, we found that it is possible to write the quantum mechanical partition function as an infinite number of integrals over position space times an exponential, together with the requirement that the position space integrals have this periodicity condition x1 is xn plus 1. Similar to what we discussed in lecture 4, it is possible to write the partition function in continuum form by introducing this continuous coordinate tau instead of the labels xi. If we do so, then we find that the partition function z is given by a constant times the path integral over x times the exponential of this particular form. The constant c is given by this expression for fixed n, m over 2 pi times epsilon to the power of n over 2. And as such, it is clear that this factor c seems to be divergent for the limit n to infinity. However, by construction, c is completely independent of any details of the potential v of x. As a physicist, it is possible for us to just ignore the fact that c is divergent since it's just a constant, and we will not worry about it. In fact, many people just don't even bother to write down the factor c in front of the path integral. Summarizing, we have that the partition function z can be written as a path integral dx over e to the minus se, where se is just this integration over tau times a function. And I will call se here the Euclidean action, and the function appearing under the integration I will call the Euclidean Lagrangian. For the moment being, these labels, action and Lagrangian, are rather mysterious. However, I will try to give some meaning to them by transforming our imaginary time variable to real time by simply setting that imaginary time tau is I times real time t. If we just do this variable replacement, we find that what I call the Lagrangian or the Euclidean Lagrangian here turns out to minus m over 2 x dot squared plus the potential term. So basically, my Euclidean Lagrangian turns out to be nothing else but minus the kinetic energy of a classical particle plus the potential energy. We can, of course, turn the argument around. If we start with the classical Lagrangian of a point particle in a potential V, then L here describes this classical Lagrangian. It's just kinetic energy minus potential energy. If we then do a transformation to imaginary time by replacing t with minus I tau, we find that we get Euclidean Lagrangian from identifying LE as minus the standard Minkowski Lagrangian evaluated at this imaginary time. There's more to this story. The action for a classical point particle is defined as the integral over time of the classical Lagrangian. If we do the same transformation to imaginary time, we find that e to the is transforms to e to the minus integral over imaginary time tau times the Euclidean Lagrangian, which is just nothing else but e to the minus the Euclidean action as I defined them up in equation 5.5. The only thing that's kind of tricky to find out in this argument is that we have to put the integration limits of the integral in the exponential tau ranging from 0 to beta basically by hand. Summarizing, if we start with the classical Lagrangian of a point particle, we get the quantum mechanical partition function z of t by writing this particular path integral here, where se is just the Euclidean version of the classical action of that point particle. Specifically, if we take e to the is, where s is the classical action, and we do this replacement here, we find that we get e to the minus s Euclidean, where c again up here is a divergent constant. And this concludes the present lecture.